Okay, so we now have a pretty solid foundation on how gases behave and why they behave that way. Key thing is that the particles are moving fast enough that whatever weak attractions would normally be between them are not able to hold them together, so they act independently. They're moving around, they're bouncing off one another, creates pressure. So if we want to quantify how much speed the gas particles have, that's called the root mean square speed. So that's the speed of a molecule. It's not the same as saying that's the kinetic energy of a molecule. So the kinetic energy is 1/2 times the mass times the speed squared. Okay, so the kinetic energy, which is ultimately determined by the temperature, that determines the average kinetic energy, that's affected by both the mass and the speed. So this is just the speed. And this formula here that's in the box includes both temperature and mass. So it's very similar to this formula. It's just a little kind of rearranged, slightly different version. So if we know the temperature, that gives me a sense of the kinetic energy. And the mass is mass, and the speed is speed. Right, so both of these formulas have the same variable. And the variables work in the same way. If I have a higher temperature, that means I have more kinetic energy on average. And more kinetic energy for a flying particle, the more kinetic energy for a flying particle, the more energy it has, could mean it's flying faster at a faster speed, or it could mean it's a slower flying particle, but it's just heavier. Right? If you get hit by me whipping a ping pong ball at you, you're probably not going to be hurt, unless your eye happens to be open, whatever. But if it's a particle that has very little mass, even if I throw it really fast and it has a high speed, it doesn't have a lot of kinetic energy. It's not going to transfer a lot of energy and do damage to you. But if I whip a golf ball at you, it might be a different story, right? Because that's a heavier particle. It has more mass, and the kinetic energy is both determined by the mass and the speed. Right? So if you know something about temperature, which was on the quiz question, choose samples at the same temperature. Don't even worry about anything else. If the question is about temperature, you know they're at the same temperature, they have to have the same average kinetic energy. The speed of the particle, though, is determined by both the temperature and the mass. The kinetic energy and the mass. Right? So this graph illustrates that. It shows that this is a distribution. So again, when we saw the simulation, we saw the particles bouncing around. Some were moving slower, some were moving faster. That's what this graph is meant to show. So we have the actual speed in meters per second on the x-axis, and on the y-axis we have the number of particles. So if we're at 100 Kelvin, which is about negative 200 Celsius roughly, that's a really cold temperature. So this yellow line here is showing the distribution of speed. So when I'm here, we're at the top of this peak, that speed in meters per second, which is about 200 meters per second, most of the molecules have that speed. Right, so wherever I have higher up on the y-axis, I'm talking about more molecules having that particular quantity of speed. And so there are very few molecules out here at this 100 Kelvin. There are very few molecules that are moving faster than 500 meters per second. Still a distribution. I still have some that are moving that fast. And no matter which temperature I'm looking at, I still have a few that are moving really slowly. So at 100 Kelvin, I have a lot more molecules that are moving like 10 meters per second or slower. Once I increase the temperature to room temperature, which is about 300 Kelvin, now the average is, instead of being about 200, shifts to about 400 meters per second. Right, so the increase in temperature gives me more speed, more kinetic energy, but I still have a distribution. But what happens to the distribution is that it broadens out. So when I increase the temperature, there's two things that happen. Not only is the average speed increasing because the average kinetic energy is increasing, also I have a greater distribution of speed. I have, especially when I go to 700, you can see it even more clearly. I still have a few that are moving really slowly. On average, they're moving faster, and I have a lot more particles that are moving really fast, up to 1,500 or more meters per second. So I get a greater distribution at a higher temperature. And so these are all for the same sample. Right? So when I have nitrogen, which has a specific mass, and I increase the temperature, I get most of the molecules moving faster, but I still have some moving slow, and I have a lot more moving really fast, so I increase the distribution. And I could use this formula to verify that. Once we talk about R, that's a constant. So when I know R, I would plug that in. If I'm using a temperature, I plug that in. I know the mass, I plug that in, and I can calculate the speed, the average speed. And again, it's a distribution, so it's not correct to say that all the particles in one sample will have the speed that I get when I calculate the answer from that formula. That gives me the average speed of the particles. So this graph is very similar, but it demonstrates the difference between three different gases at the same temperature. So these are all at room temperature, and what you see is the lighter the gas, the faster the speed on average, and the greater the distribution. Similar shapes to the distribution. Broad distribution when things are moving faster. So the helium is so much lighter than the chlorine that on average it's moving a lot faster. So which has more kinetic energy here? The helium or the chlorine? How many people say helium? How many people say chlorine? How many people say they're the same? Awesome. Good job. Right, they're the same, right? Because they're at the same temperature, they have to have the same average kinetic energy. So the light particles on average are flying faster, and the heavier particles are flying slower, but if you get hit by those, they provide the same quantity of energy, or same kinetic energy, or same force, because they're at the same temperature. Any questions about that? 11.6. It's got a few gases and pictures there. One of the gases is uranium hexafluoride. The other is just 2 fluorines in a molecule, and the other is nitrogen with 3 fluorines. It says we've got these 3 gases. Which of the 3 gases will have the highest root mean square speed? Can I really answer that question? If I only know the identity of the gases and I want to know which has a higher speed, I can't really answer that. I need more information. What information do I need? I need to know something about the temperature. It's possible that the lighter molecule could be moving slower than the heavier molecule if it were at a much lower temperature. So we're talking about the average speeds right now. If they're at the same temperature, though, then they have the same kinetic energy. So if they have the same kinetic energy, if one is heavier, it needs to be moving slower than the one that's lighter. It needs to be moving faster. So if we know they're at the same temperature, then the one that's lighter would have a faster average speed. If they're at the same temperature, which has the highest average kinetic energy? They're the same. They're at the same temperature. Okay? If we wanted to determine quantitatively how much faster, if they're at the same temperature, they have the same average kinetic energy, which is determined by both the mass and the speed. If they have the same kinetic energy, we know the one with less mass has to have more speed, so when we multiply, we get the same value for kinetic energy we do for the one with more mass. But if we want to know how much, then we can use the formula that we talked about. So this formula is a ratio. It tells me the speed of one substance, depending on its mass, versus the speed of another substance, depending on its mass. And so if I have two substances, we've got helium versus carbon dioxide. Now we know for a formula how to figure out that mass. I would add the mass of one carbon and two oxygens to get the mass, average mass of the carbon dioxide molecule. So instead of working with these units, let's just keep working with AMU. So this is the mass of helium. This is the mass of CO2. So then I would plug those in. So we'll keep these units. Plug those into the formula, right? So the helium is going to be the lighter one. I probably want to make that one on top here. That's going to give me a number that's greater than 1 and more relatable to me. So I take the lighter substance. That means its mass goes on the bottom on the other side. The heavier substance on the bottom on the left, its mass is going to be on the top on the right hand side. Right, so I'm just plugging into this formula, put these numbers in my calculator, divide them, take the square root, and I get 3.316. So that means if they're at the same temperature, on average, a helium atom is moving about 3.3 times faster than the average carbon dioxide molecule.